Okay, so this is my final submission for the game engine. So just before I go ahead and run through the code, I'll just quickly give the demo of what I've been working on. So my demo game right now, the player controls the frigate model. There's a bunch of tanks that are moving around shooting their own bullets. As the player, you can press the enter space to fire your own bullets back at them. And once you destroy all the tanks in the scene will change to another one, and you can go ahead and kill all of the tanks in that one as well. And once you do that, it'll go ahead and take you back to the first scene. So it kind of just loops between the first two scenes right now. Now, as you just saw, if you get hit by a bullet, the game will kind of just restart. You'll just kind of restart at the current level you're on at the moment. So that's pretty much all set with the demo right now. So let me just also go through the debug code real quick just to kind of demonstrate the destruction of all our items. Let's see here. Okay. So basically, when we start right away, we do have a pointer to our null scene right before the user scene is created. We delete all of our scene level managers, so we have updatable, drawable, alarmable, our keyboard events, collision manager, our registration broker, and the camera manager as well. Then when we actually create our level 1 scene, we have all the type IDs for each instance of all of our collidable objects. And then, of course, we press the enter key, representing the key press. And then when we delete our scene, we kind of just delete all of our objects, as well as each of their commands that they require for the game objects there. Deleting our factories, going through each of those, and again, deleting our scene level managers. And that pretty much just goes on for all of the scenes. The scene swaps work just fine. And then at the very bottom, when we finally finish everything else, we will delete all of our asset managers inside of our engine, delete the last scene that is there, and then also get rid of our scene manager, time manager, and visualizer, and our Atom engine pointer, since there's all engine level components there. So let's go ahead now and go through this code as quickly as we can. So basically, starting with our engine class, it's pretty straightforward. It is set up as a singleton derived from the base engine class. There are some public methods down here for the user to access the window name and set the window height and that kind of stuff. Inside of our engine class, it's completely stripped of any user code, so they don't have to touch this. Initialize, where we initialize any user content, and we also load any of the user's assets and set the first scene, and actually initialize this first scene here. Update and draw, we update and draw the current scene in the scene manager and also update our time. And then unload content, basically get rid of everything. Clean up all our assets, clean the current scene, destroy our time manager and our visualizer, as well as unload any user content that needs to be destroyed here. And going inside of the user content class as well, again, pretty straightforward, just 3 different functions that the user is able to access completely separate from the engine. So again, game initialize, pretty straightforward. The user can set up some pretty standard settings, setting the device, the window name and the height. Load resources, they load any of the models, textures, and shaders that they require. I'll go into those specifically. Basically, they just kind of assign a custom name, and then they load those assets through a variety of ways. They set the current scene, and then they unload any content that needs to be unloaded there. So I think that's all set for the engine. So let's go ahead into our asset managers now. They're all very similar. So our model manager, set up as a singleton at the engine level. It will locate any models with the file path from the models folder inside the project. All of our asset managers are using dictionaries. Now the reason for that is that each asset really only needs one key value pair, because we don't want the user to accidentally make 2 different assets with the same kind of with the same custom name or anything like that. Now with the model manager, we can load models either through a given model name using the file path and creating it, or with a specific pre-made model as well. Now, I also have some assert functions to help the user let them know that when they make their custom name, to make sure that there is no error, that they don't use the same name twice. So when they create the custom name, it will check to make sure that it does not have a corresponding value. So for instance, as an example, if the user did decide that they wanted to get they were loading one model, but they gave it the same name, access, they're loading it twice, we should get some kind of error thrown here. Yeah, there we go. So the model manager threw us an error saying that the custom name, there is actually already a value assigned to access, and we use the same name twice. And then likewise, going back into our model manager, whenever we get our asset that is available, it will also make sure that the custom name does have a value assigned to it. So for instance, if there is a case where the user is loading one of their assets, say loading one of the textures, they accidentally mistype the name here when they're getting it, we should get an error thrown, saying that the custom name should have been set to something, but it does not have a value in its dictionary. And then, of course, the model manager, when we unload it, will go through the dictionary, delete all the pointers, and of course get rid of the pointer to the manager itself. And then again, the shader manager and the texture manager are very similar, using the dictionary, the file path as shaders. And of course, the load and the get functions are all public for the user to be able to use. But anything such as the unload or such as the unload functions is only available through the attorney class. And then again, with the loading for shaders, we basically just load from a file name here. And then the texture managers, again, the file path is the textures folder. We can load the textures either from an asset name or from a given RGB value to get a certain color. And just quickly touching on the attorneys as well. The point of the attorneys is to kind of restrict certain functions away from access from the user. So for instance, for the shader managers and for all the asset managers, a lot of them are engine level, and the unload functions to actually destroy all of their contents should really only be accessed by the Atom engine itself. So, going back to the Atom engine, as you can see, when we clean up the asset managers, we go through the attorneys to actually call the unload functions. Now, the user obviously has access to the asset managers, like let's say the model manager. When we call it, though, we can only call the get and the load functions. We are not able to call the unload functions. So the attorneys kind of help streamline that process there of what is accessible to the user and what isn't. So I think asset managers are all set. Let's go through time manager real quick. So it's pretty straightforward. Also set up as a singleton at the engine level. Its basic responsibility is just to hold on to game time and frame time and calculate that every single frame. The user has access to those to get frame time and total time as well. So basically, every frame will just calculate the game time with our freeze time class, and then frame time is the game time minus the previous time. So looking at our freeze time class, basically, the function of this is to be able to calculate the game time correctly, even if we decide to use the debugging tool and completely freeze the game with these function keys. So even if the game is completely frozen, it will correctly calculate the game time itself. So if we go ahead and test that real quick, just go ahead and start running this again. So let's go ahead and press the F10 key, and we can see that the game itself is completely frozen now. At the bottom, our freeze frame, we are like 6 seconds. So even though the application itself is running for about 20 seconds now. We're only stuck at 6 seconds. So if we go ahead and actually press F9, that'll keep progressing everything by 1 frame, and it'll correctly keep the game time intact. So that is all set, I believe. All right, let's go ahead on to scene management. So the scene manager is pretty straightforward. Of course, set up as a singleton. Its main responsibility is just updating and drawing the current scene, but also processing any scene change requests by the user. So of course, the user can set the next scene and also get the current scene. And the scene manager kind of holds on to its own list of commands without using its own broker. So when the scene manager starts, we basically have a null scene pointer, just held there until the user actually fulfills their own request for the scene. And then whenever a scene change is requested by the user, we will first call the scene end function for our scene, delete all the content inside of it, delete the pointer to that scene. Then we will assign our new pointer to our current scene and actually go ahead and initialize that. But first, when that is processed, to actually process the set next scene, we actually have a pointer to our scene change command, which will go ahead and actually process that request. So we'll put that in a list of commands, and then on the time that we update for the next frame, we'll go ahead, go through that list and execute that command. So let me just quickly show that command as well. Yeah, so our scene change command is all down here. Basically, we just pass in the parameters to set our new scene, set the scene, and then when we execute it, we'll go through the scene manager attorney to call that there. So yeah, again, scene manager, pretty straightforward. And then our scene class, the user will go ahead and override the initialize and scene end functions for their specific scene. It's also responsible for registering and deregistering all the different game objects to the scene. So the scene has all of these scene level managers for managing the game object registration. So when we update, we will first process any commands for registering and deregistering game objects. Then we'll check for alarms, collisions, keyboard inputs, and then update any of our objects. And then, of course, we'll draw our objects as well. We also have a quick shortcut to our camera manager to get the current camera from there. And then, of course, all of our functions to register and deregister our game objects there. And then just looking at one of an examples of the scenes here real quick. So our first scene that we load, we have our initialize and scene end functions. Pretty straightforward. The user basically just creates all of the objects they need here. So we have a couple pointers. We have a factory here making some objects. This is where we also set our collision pairs that we want to test in this specific scene, which I'll be getting back to shortly. And then when the scene ends, we'll go ahead and delete any of the objects that we created in there. So that is all pretty straightforward. I think we covered everything there. Yeah, and just going through just quickly showing the collision pair as well. Yeah, we basically just go through our collision manager. We create a dispatch. I'll get to that. I'll get to that shortly. So, all right. So yeah, let's go ahead and start going through all of these game object systems. Let's just check our time real quick. All right, wonderful. So update and draw are the first ones we'll cover. They are very, very similar and very straightforward. So basically, all they're worried about is just kind of responsible for keeping a list of all the objects that simply need to be updated. We have our functions to submit for registration and actually register. There are commands for registering and deregistering. Just one pointer for each game object, so we don't have to reuse those every single time. And then this delete ref is basically holds on to the position of the game object in its update list, so that when we delete that object, we can use that reference to easily locate it in the list very quickly and efficiently. So basically, and a lot of these registration functions are going to be very similar, but basically how it works is that we'll assert that the current registration state is set to deregistered, which is the case when we start right away. And if the object hasn't been initialized, we will create our registration commands. Then we will call our scene attorney, put in our registration request. So actually looking at this one specifically. So for instance, the update registration request, we just pass in the pointer to the object. And once it's time for the scene to execute that command, we will call that pointer and actually register it. So when we actually register it, we'll go through our update manager and register. And likewise, same thing for deregistration as well. So looking at the update manager, we basically just have a list of all of our updatable objects. So when we register the object, we'll add it into the end of the list, hold on to its position so we can delete it easily when we deregister. And we simply, each frame, we simply go through that list and update all the objects inside. And again, drawable manager, very, very similar. We just have our register, deregister commands. We'll go through it. Pretty much the same thing as the updatable manager. Again, we just have a simple list of all of our objects, have a reference to its place there, and just simply iterate through the list and take care of that. And of course, the draw registration is pretty much the same thing. Just pass in the pointer to the object, and then we're all set to go. Now, I think we can look at the alarms next. Now, the alarms are a bit more complicated. Basically, the user has 5 different alarm functions that can be triggered at different times. So depending on that, because they are so complex, the registration for alarms, it's actually tied to the alarms themselves and not the game object. So because of that, each alarm will hold on to its own registration commands and registration state, as well as its reference kind of in its own list. So looking at our alarmable class, when we actually delete everything, we'll kind of go through all of the alarms and take care of all those commands. When an alarm is triggered, we'll find the alarm ID and trigger the respective alarm function. When we submit for alarm registration, we'll make sure the alarm number is not higher than the max alarm number. And then we will go ahead, and this is where the user also passes in the duration of time that the alarm will last, and we'll set that for the registration command. If I can actually pull that up. Just give me 1 second, let me find that. So our alarm registration command, this is all set up. Everything is passed in. We pass in the alarm ID, we set the time, and then we'll actually register it. And again, all of this, when we deregister, just make sure the alarm number isn't greater than the max alarm number. Pretty much the same thing. But we are always passing in the alarm number because the registration is specific to each alarm. And then inside of our alarm manager, we are using a multi-map to track all of our alarms. The reason being is that there can be multiple alarms triggered at the same exact time, so there can be multiple events for one key value of time. So when we register, currently we're just using insertion sort. All the timestamps are sorted in an ascending order. And of course we have our reference to easily get rid of it as well. And then when we process for alarms, we will get the first timestamp in the list, and we will see if it is smaller, if it is a shorter time than the total time of the game, then we'll go ahead and trigger the alarm for that object and get rid of that timestamp in the list. And then I think the alarms are all set, so let's go ahead to inputable next. Inputable tracks the key event pairs. Currently, right now, it's just for key presses and key releases. So again, this one is a little more complex as well. We have registration and deregistration commands pretty much set for each specific kind of key event pair that we're looking at. So, looking at our registration command, we'll pass in our key and event, and then we'll register that. So so each key event pair will have its own registration command. And then going through now there are actually two managers for inputables. The first level that we go down to is simply our keyboard event manager. It will basically hold on to the map, just kind of a very simple map of all the individual keys that are currently requested to have events for. So when we register for a specific key, we'll see if that key has a value yet in our map, and if it doesn't, we will create a new single key event manager to manage all the events for that specific key. And then when we actually go in and process that, our single key event manager just simply manages all of the events for that specific key. So for instance, when we do a key press event and the key down boolean was set to false, we'll set it to true, call the key pressed event, and then likewise, if the key is released and key down is set to true, set it to false, call the key released event. So I think that's it for inputable as well. And then let's go ahead and try to get into collision. I think we're doing okay on time. So collidable, there's kind of a lot going on in here. So basically, each collidable object really only needs to manage, I believe it really only needs to manage its own registration and deregistration command. So that part is actually pretty straightforward. Now, whenever we have an object, we also have a collision ID. So basically that is kind of tied to, the ID is specifically tied to the individual type of class. So like for instance, the bullets will all share the same ID. There can be 100 different bullets, but they will all be the same exact ID. So all of those instances of the bullets would actually be stored in a collidable group. Basically, it is just a list of collidable objects, but they are all of the same type. So all the bullets would be in one collidable group that is managed. So our collision manager basically holds on to a list of all the collidable groups here. And then our set collision pair, this is called by our scene whenever we want to test a pair between two different objects. We'll go ahead and create a new test pair command. And then once we execute the command, so basically our collision manager, when we execute this command, basically we will go through, just to give an example here. So for instance, we want to detect collision between bullets and the enemy tanks. So in this example, let's say collection 1 will be the bullets, collection 2 will be all the instances of the enemy tanks. So basically it's going to go through all the instances, all the possible combinations of those, and it will check to see whether or not their B spheres collide if they intersect, which does actually quickly take us into our math tools class that I'll quickly demonstrate as well while we're on the topic. So PW math tools, it's just a simple class with a bunch of static methods that can be utilized. This uses the collision volume B sphere, the intersect function, collision volume B sphere, to detect whether or not the objects are colliding. So it'll basically find the distance between, it'll find the distance between the 2 points, between the 2 centers of the object. And if that distance between the 2 centers is less than the sum of those objects' radii, then it will determine that those objects are in fact intersecting. And if it is, then we will go ahead and call the process callbacks function, at which point we will call the collision functions for each of those objects that are intersecting. So I think that's it for collision. Game object life cycle. So in some cases, the game objects may want to exit or enter the scene at will before the scene itself is done. So looking at the game object real quick, we have the scene entry and scene exit functions that will be filled by the user. Of course, we have a registration and deregistration commands as well. Again, very similar to some of these other ones before. So basically, when we submit for entry, we will submit a command to our scene to submit that object for entry. And then once we connect it to the scene, we will go ahead into the object itself, call the scene entry function. Scene entry and scene exit are user defined. They will figure out what the object wants to do in there. Basically, in those functions, the object will actually go ahead and kind of register and deregister for all of its things. So for instance, looking at the frigate, when it has its own scene entry, it will register for all its update and drawable and its inputable events and collision. And likewise, when it exits the scene, it will go ahead and deregister at that point as well. Let's take a look at that. And yeah, just quickly looking at the commands. So again, we just simply pass in the pointer for the object for entry, and then when that request is called, we'll call it to connect to scene. Are there any other things? I also just want to quickly go through the objects themselves. Also just quickly demonstrating the visualizer as well. So the visualizer is used specifically right now to visualize the collision volume sphere. So show volume sphere, when that is called, we'll pass in the collision volume sphere from a collidable object. We will calculate the matrix of that object based on, we'll calculate the world matrix based on that collision sphere's radius and center, and then we will actually go ahead and render that sphere with the world matrix and the color that the user passes in. So just to demonstrate that real quick, let me go ahead and I will actually try to turn that on here. So I'll turn that on for the frigate. You also find our enemy tanks. We turn the visualizer on. And basically what we should see, we should simply see some spheres popping up around the objects. Yeah, there we go. So that'll show whether or not they are actually colliding. The frigate actually has a pretty big sphere here. But yeah, so that just kind of helps for debugging purposes just to show those. But that is in fact working. And then I think that's pretty much it. And then just to quickly go through just the classes that I'm using for the game itself real quick. So the frigate, again, utilizes a lot of these functions: scene entry, update draw, the alarm functions. So it calculates its scale, rotation, position. We create a graphic object, getting all of our assets required. We will set our collider model for the B sphere, and this is where we'll also set our collidable group for the frigate. So this is where the my ID is set, the my IDs that are printed out, the type IDs that are printed out. Then we'll submit it for entry, register it for the scene. And then basically when we update it, we'll check for the key presses to rotate and move around, update the world matrix. Of course, our alarm functions are called here. Well, these are just some test alarm functions, but we also have our key press events to check. So when we press the enter key, we call the bullet factory to create a bullet with the rotation and the position passed in with the offset. And then when it collides with an enemy bullet, we'll call the enemy bullet to submit exit, and the frigate will submit exit as well. And then let me just also show one of these bullets. The bullet and the enemy bullet are very, very similar. So, we create those, and basically every frame, it just goes through and moves forward. Scene entry, again, we just set the collider model. We register it for all of its functionality, and on scene exit, we'll go ahead and deregister it for everything. So, and then inside of our bullet factory as well, we can see, so the bullet factory, all the factories are very similar. Set up as a singleton, holds on to two different lists of the bullets here. So we have recycled items and the current active items. So the user can terminate that. They can also create or recycle bullets whenever they need to. So when we create a bullet, we will see if the recycled items list is empty. If it is, we'll create a brand new bullet object. Otherwise, we will use a recycled bullet object, and then we'll push that item to the back of the active items. We'll initialize it, then submit it for entry. And then when we recycle the bullet, this is actually called by the user, we will remove it from our active items and push it to our recycled items list. And then once the bullet factory is actually terminated, we will delete all of our bullets inside of all of those lists, and then delete the factory itself. And I think that is pretty much it.